But first of all, taking a look at, there's a formula here, a relationship between x and y that's defined. X squared plus y cubed minus 2xy equals 7. And a graph that goes with it. Meaning, again, in this display, every part of this magenta curved something composed of infinitely many individual points. All of those points are xy pairs that make the statement true, just like any graph. It's just this one, it's not the y isn't a function of x in this relationship. If you can see, maybe thinking about how on earth would I try to get y equals out of this without having y's on the other side, or also just looking at the shape of this, visually speaking, I can see that for at least a few values between like 2 and 4, there are several places where x values in this range right here correspond to a few different possible y values. So like x equals 2, there seems to be a point down here at negative 1.5, and another point up here at a little bit over 2. Or maybe at x equals 3, there's a few different points on the graph when x equals 3. So this isn't a relationship where y is a function of x, where y is completely determined by the input x value that's given, but we can still describe this set of points. That doesn't mean it's not good, it just means it's not something that has that description, y is a function of x. Nor is x a function of y. It doesn't work the other way around either. If I give you a y value, you can't just tell me which x value I'm talking about. But there is this relationship that tells us all the sorts of points that are on here. So if I make up an x value, I can solve for the y value or the multiple y values that go with that and make this equation true. And vice versa, I could make up x value, or make up y values just as easily and maybe solve for the x that goes with them. But thinking about how this relates to what we've been working with, derivatives, rates of change, and uses of those, even though this isn't in the normal arrangement of terms, y equals and stuff with x, or f of x equals and stuff with x, we should still be able to describe relative rate of change for y and x, because you can see, like looking at this, as I move from left to right, if I were increasing x, y is increasing here. And then as I continue increasing x, y increases. And well, if I just describe the x value at this point, there's a few different things going on, but I can talk about the coordinate points, the locations on this graph, and the relative changes in x and y at those xy locations. So when I have these negative x values, and if I zoom out, the ends of this graph aren't particularly interesting. They just kind of keep going like that. Just this central part is a little weird. But if I describe fully, like using an xy coordinate pair, I can talk about the relative changes in those. So if I'm thinking about this spot right near the x-axis when x equals 3, just a little bit above. If I'm thinking about, well, if I increase x by a little bit, so not following the path and going back around to the left, but if I'm at this spot, let me grab a pen thing. So let me scoot this, please. There we go. So if I'm right around here, if I increase x a little bit, I can see that y increases. If I'm at this x spot that has the same x value but a different y value, I can see if I increase x a little bit, y decreases maybe a little. Or if I was at the same x value but down here, I can see, well, if I increase x a little, y decreases, well, more than it does up here. I should be able to describe dy dx, dy over dx are the relative changes in x and y, whether or not I have something that qualifies as a function, as long as I specify coordinate pairs as opposed to just individual points. If you have something where y is a function of x, given the x value, that's enough because there's only one spot on the graph, there's only one y value that pertains to that anyway. But in something like this, which isn't that y is a function of x, we should still be able to describe what's going on. So what we're going to work on today, we're going to talk about how to find derivatives when we have expressions in this form. And you can find dy with respect to dx, or just as easily dx with respect to dy. But to keep the ratios in the order that we're used to, we'll just do dy with respect to dx, changes in y with respect to changes in x. You don't have to have the equations solved for a variable to do that. What we end up doing is using chain rule. So let's take a look at the general technique for that, and then after we do this with just these general sorts of equations, we'll see some other ways that we can use kind of variations on a theme with chain rule. It's really just using chain rule in maybe unexpected ways to help us solve a few new types of problems, including proving some of our derivative rules. So let me get this out of the way. Just open up this. Where is it? All right, so this is the graph we just saw. Scoot this guy, maybe. So as I was talking about, this graph and the equation represent the same things, one visually and one just in equation format, the corresponding pairs of x's and y's. So one visually representing where all the different pairs of values are for x and y that make this equation true. The equation does it by, you could guess and check, pick some numbers and see. They both represent the same sets of ordered pairs in that way, just one shows you them and the other one tells you how they're formed. They make the equation true, and when they're plotted in a plane, all points form that curve. So we talked about y is not a function of x here, based on the rules for that. Y would have to be completely determined by x. Anytime I pick an x, you know the one at most possible y value. So we can still talk about the changes, though, like I was talking about earlier, if we're careful about it. We should, in fact, be able to come up with a rate function. So, because at any point, even though this doesn't fit our normal definition of what we're working with before, we should be able to describe those changes as long as we give you the location. So, I'm going to try to find the best spot for this. All right, it's out of the way. So, here we go. I'm just going to put it over the edge here. There. So in order to determine dy dx, we're going to pretend that y is a function of x. So I can even, instead of using the letter y, I'm going to use the letter f of x. And in that sense, we have this f of x or this whole other function kind of jumbled in among everything else. Yeah? Yeah, that's what, visually to describe something that isn't a function, y isn't a function of x if it doesn't pass this vertical line test. But in the end, it doesn't really matter whether it passes a vertical line test or not. We can find derivatives. So that's our cool thing for today, that we're going to figure out how we can do this without trying to make it look like y equals something, even if it had like a plus or minus or something else. But what we're going to do is pretend that y is a function of x just symbolically, so we can think about how derivative rules work. Meaning, what I'm going to do is I'm going to write f of x instead of y, even though it's really not a function of x, but I'm going to use the symbol so that we can think about our derivative rules and chain rule in specific with an inner function and an outer function. So this is called implicit differentiation. What's meant by that is we're implying that y is a function of x. It's not in reality, but in the end it doesn't matter whether it is or isn't a function of x. We can find the derivatives the same way. So what we do, if our original function, we have this x squared plus y cubed minus 2xy equals 7. We're not going to try to solve for anything here. I'm just going to replace the y's, y appears twice, with f of x. So if I were able to solve this and have y equals and then a bunch of stuff with x in it, I could call that y f of x. Y is a function of x. And so this y in the middle here would be a whole function of x that's cubed. Now, it doesn't meet the definition of function, but that's okay. I'll just say it's a relation in terms of x. But the second line here is just the same thing. I just replaced this symbolically, and this is just to relate it to other things purposes. It doesn't really change what we just did. But if I rewrite this as x squared plus f of x cubed, thinking of y as the dependent variable of this relationship, even though it doesn't really matter which one you consider independent or dependent, minus 2x times f of x equals 7. So it doesn't say equals y, it says just equals 7. But if I think about this, I've got this expression, and each individual term of this expression is something that we've taken derivatives of before. Now, normally we had actual function written, like some whole formula cubed, as opposed to writing f of x cubed. But when we were talking about chain rule the first time, we talked about how to think of, oh, there's this whole inner function, call it f of x, and if I have to take the derivative of some function, some whole formula to the third power, then, well, we just use we use chain rule. We use our power rule 3 times the original f of x squared, and then times the derivative of f of x. And I can differentiate each term in this expression, including the 7, and thinking kind of algebra logic-wise, I have an equation right now. The left-hand side and the right-hand side are equal at all points. So that must mean that if I differentiate both sides, find the rate of change of both sides, those must also be identical because, well, if the two sides are equal, then their rates of change must be equal. They can't have two different values and not have the same rate of change. I know the rate of change of the right-hand side, though, is 0. The derivative with respect to x is the rate of change I'm talking about. If I take the rate of change of 7, that's 0. All the other terms, well, the first one is simple. The derivative with respect to x of x squared, that's a 2x. This f of x cubed looks a little weird, but it's just, I'll just write it like chain rule. 3 f of x squared times the derivative of f of x, f prime, right? So the tricky part is going to be this third term inside the parentheses here, the third term from the left side, this 2xy originally, now written as 2x times f of x. Well, if I have a derivative of 2x times some other formula, I'm going to use product rule. So derivative of 2x, well, minus 2x would be negative 2 times the original f of x plus the original negative 2x times the derivative of f of x. So just differentiating each side, let me rewrite that. We had, because this is being stubborn today, let's see. So we had x squared plus y cubed minus 2xy equals 7. So if I do the same, I'm just rewriting what was just up there. So if I write x squared plus y cubed it was, sorry. F of x cubed minus 2x times f of x equals 7, and take the derivative of each side of this expression with respect to x. Let's just scoot this over a little bit. Then on the left-hand side, this x squared becomes 2x. The derivative of f of x to the third power with respect to x. Well, if I knew what function f of x was, that would be great, but even without knowing what it is, just general chain rule, the derivative of something cubed is 3 times that something squared times the derivative of the inner function, which is f prime of x, right? So even though I don't know what f of x is, I can write its derivative. Now, f of x, I just replace the letter y with f of x. So this is really the same as y prime, if you want. This third term here, I'm going to use power rule with it. So I've got 2x, or rather negative 2x, times f of x. And I know how to find the derivative of either of those with respect to x individually, 2 or negative 2, depending on how you want to group this with parentheses or with the negative inside or outside. And the derivative of f of x, well, f prime of x. So using product rule, I'm going to have, I'll use the negative as a part of this. So I get negative 2 times the original f of x plus the original negative 2x times the derivative of f of x. So that's f prime of x. And that's differentiating with respect to x, each of the terms on the left-hand side. And then on the right-hand side, the derivative of 7 with respect to x, it's a constant. So its rate of change is 0. So if our goal is to find the rate of change of y with respect to x, which I changed the notation so we could also call that find f prime of x. Again, thinking back to directions you probably saw in algebra class. You see a big equation, there's x's all over the place, and it says find x. It's like, oh, well, I need to solve for it. Well, find dy dx or f prime of x. In the original, it didn't exist. It wasn't in here anywhere. But in this expression, I see f prime of x, otherwise known as dy dx or y prime, in that expression. All I have to do to find it is isolate it. So this equation, if you notice, because of how chain rule works, f prime of x isn't to the third power or anything like that. It's just multiplied on as a linear factor, tagged onto a couple of terms. So solving for f prime of x is just a matter of, oh, I can factor it out and move everything that doesn't have f prime to the other side of the equation, like subtract and divide sorts of solving. So I've got in this expression here on the left-hand side 1, 2, 3, 4 terms across the equal sign from 0, but kind of sorting through, and this is all algebra from here. We're done with the calculus part, but the algebra is just a little messy, so I'll show you a couple times. So I've got this term, which has an f prime in it, and this term, which has an f prime of x in it. The other two terms don't. So they're not precisely like terms, but I'm going to move these both over to the right-hand side of the equation where there's currently a 0. And these two terms that have f prime of x in them, I'm going to leave them on the left-hand side, but factor out f prime of x from them. So from this term, that leaves 3f of x squared. And from this term, that leaves minus 2x. So on the other side, just scooting stuff around the equal sign as usual in algebra, add this term, so I get a positive 2f of x, and subtract this, so I get a minus 2x. So 2f of x minus 2x. F prime of x times this quantity in brackets equals this expression. So solve for f prime of x at this point is just divide by the brackets expression. And so f prime of x, I'm going to translate this back into y's in a minute, is 2f of x minus 2x over this stuff. 3f of x squared minus 2x, which, if I put this back in the original x's and y's, y prime or dy dx could be this left-hand side, f prime of x, and f of x, well, I just use f of x instead of the symbol y, just to imply the fact that y is a function of x, or so we can think about this in terms of chain rule, because we're finding a derivative with respect to x, and so we're thinking of y as a relation where x is the input and y is the output. It's just not specifically a function. But rewriting this, then I'd have 2y minus 2x over 3y squared minus 2x. And you can't cancel those out because they're not factors, they're terms. But notice that this expression for the rate of change of y with respect to x involves both x's and y's in its formula. But that's good, because if you remember the graph we were looking at, in order to specify which point you're talking about, you'd need to specify an xy location. There's places to substitute in both the x and the y part of the coordinate point, the correspondence point, in order to think about that. So there was one point in there that looked like it was about, let's see if I can pull up that graph again. Let me, not with this window here. It wants to take this away from me. So I'm going to have to close this window out that has all of this on here. 2y minus 2x, 3y squared minus 2x. All right, so oh, come on. Y prime. Y squared minus 2x, or no, 2y minus 2x over 3y squared minus 2x. So that's our derivative equation for this. Let me scoot this a bit. So if I'm looking at this point, like we could use the original equation to solve for the exact points, but just using quick estimation, I say, well, this point here, it's about 2, 2 1/4. if I think about the value of this, and this is supposed to be minus, if I think about the value of this expression there, I'd expect it to be close to 0, maybe a little negative. And I can see if I put in 2y and 2x, okay, the numerator is going to be a little bit positive. So it would be 4.5 minus 4 over 3y squared, 2.25 squared. Don't know what that is off the top of my head. 2 1/4 is 9/4 squared. 81 over 16 is 5 point something. Oh, times 3. Yeah. Oh, sorry. Thank you. Sorry, I was using a point that I was thinking of earlier. So I looked at the 2's first when we were doing the other side. Thank you. So this will be minus 2 times 3. And then 3y squared is 15 point something minus 2 times 3, 6. So 15 point, not quite sure what, but this would be negative 1.5 over positive something. So it's going to be a proper fraction, meaning the denominator is larger than the numerator, so it's fairly close to 0, but it will be something negative. Just estimating points on the graph. Like I said, you can actually solve for what are exact points. It might not be that exact point. On the other hand, if I were to pick this point like 3, what is that, negative 2.75? And use that, I can see, well, the 3 part's the same. So these are going to be minus 6's there. But with a y value of negative 2.75, I'm going to have a negative on the top, and this is going to, well, this is going to be much larger here. So I have a negative minus a negative, and this is going to be much larger than before, but I'm still going to have a negative proper fraction. If I pick this value in between with very small y values, these first 2 parts here are both going to be small. I'll end up with a negative over a negative, which would be positive. So just in terms of, it does match up with the graph. You can check for precise points and do some computations if you want, but just the idea is that even though this relationship between x and y isn't solved for y, that doesn't mean that we can't find the rate of change between x and y. So how many y's per x, it changes that. And in fact, the solving, because of how chain rule works, always ends up to be this same sort of, oh, just factor out this f prime of x or factor out this y prime. You can just write it as y prime. You can write it as dy dx. You don't have to insert this f of x feature into it. I just did that so that you can think of how that relates to the rule for chain rule that we started out talking about. So let me show you with some much simpler sorts of questions, really what this is doing. So let me clear this off. So suppose I have just something that could easily be solved for y. Something like 2x plus 5y equals 12, right? This linear function. I could easily solve this for y. I can find dy dx by solving and getting y equals, subtract and divide, negative 2x divided by 5 and 12 divided by 5, right? So we'd have, these are equivalent to one another, just subtracting and dividing. If I wanted to find y prime from this, it's like, okay, regular derivative rules. I've got this function of x over here. Here's a linear term. The rate of change is its coefficient, otherwise known as the slope of our line. Constant goes away. In this form, we will get the same result if I find the derivative with respect to x of each term on both the left and the right-hand sides. I'm going to put this afterward just to save space. But the derivative with respect to x of a constant is 0. With respect to x of 2x, well, that's 2. And think of this as 5 f of x. It's a coefficient on a function f of x. What's the derivative of that? We're not finding a derivative with respect to y. So finding the derivatives of these 2 terms isn't the same. This is our normal derivative, and this is a chain rule derivative, because think of y as a whole other formula. It's got a coefficient of 5, but we need to know what the derivative of that other formula is. Y prime or f prime of x. or dy dx. But if our goal is to find, normally in the past we said find the derivative, or find the derivative of y with respect to x. Well, we're not done at this point. We've differentiated the terms, but because of the way that this expression was structured, that when we're done, the y prime isn't found, it's there, but I need to subtract and divide. Subtract 2 and divide by 5 to isolate it. And note it's even the same steps, subtract and divide. So we get the same results. This is useful for, not particularly for this, because no one would probably sit and do this weird way when it's easy enough to solve for y. But if you have not even extremely strange equations, but just something like x squared plus y squared equals 100. This is a circle centered at the origin with radius 10. We should be able to describe rates of change of y with respect to x around that circle. And if I think of this maybe x squared plus f of x squared equals 100. I mean, this one, I could solve it for y. Y equals plus or minus the square root of 100 minus x squared. But thinking about difficulty level of derivatives, this is slightly unpleasant. Plus it has a plus and minus, which is a little weird. This one, if I think about finding a derivative with respect to x, I get 2x plus derivative with respect to x of this, 2f of x times the derivative of the inside function, f prime. So this is taking the derivative of each side. And if I solve for f prime of x here, it's subtract and divide. Subtract the 2x, divide by 2f of x. Or in other words, f prime of x is negative 2x over f of x, otherwise known as 2y. This is easily simplifiable. Those are factors of 2. Y prime, oops, that's supposed to be an arrow. Y prime equals negative x over y. Thinking about circles centered at the origin, like this is the point 10, 0. Circle centered at the origin, radius of 10. I can see that, yeah, at that point, the rate of change of y with respect to x is undefined, negative 10 over 0. That makes sense if I think about, well, if I increase x, well, you can't really increase x from here, but if I change x somehow by staying on this path, y essentially goes straight up and down. That's not a rate of change, that's this 10 to 0 ratio. That's bad. If I'm at a spot like here at the top of the circle, 0, 10, on the other hand, 0 for x, 10 for y, that just comes out to be a rate of change of 0, which that also makes sense, visually speaking, matching the circle. If I were to pick something in the first quadrant, I can see, oh, a positive x and a positive y value. This would come out to be negative some sort of fraction. That seems reasonable for negative something while I'm in the first quadrant in terms of thinking tangent lines, or as I move x to the right, my y would be decreasing. Versus if I were down in the fourth quadrant, thinking about an x value down here, a positive x with a negative y, that makes that equation true. A positive value over a negative value with a negative sign in addition would make a positive result. And thinking about being down here, if I increase my x value, my y value would increase. It's a positive rate of change. Without getting into the specifics of the numbers, I just want to kind of visually show that. But just the point is that if you have your x's and y's jumbled in an equation, or just it isn't solved for y, that doesn't mean you're stuck in terms of solving for a derivative. It doesn't mean you have to solve for y to find a derivative, although if you can, you certainly are welcome to. If you have something that has the x and y's jumbled and you find the derivative by differentiating each side of the relationship, just realize your dy dx or y prime or whatever symbol you're using is going to be also jumbled, and you're going to have to solve for it. And typically, not always, but typically you're going to have that rate of change involved then by the time you're done, both x's and y's, which that's okay, because in these cases where you have things that aren't standard y is a function of x relationships, you need to define both the x and the y point values in order to describe which point you're talking about, which part of the relationship you're talking about. So another time this comes in handy is a way that we can prove some of our derivative rules, like power rule, for instance. We kind of looked at a pattern for why it works with whole numbers, and we also did a negative one, or we did a 1/2 power from scratch. But we can actually use this idea of implicit differentiation, or differentiating things where it's not solved for y, in order to find the derivative of, well, not y equals x to the n, but a different algebraic form of that. So thinking back to algebra, y equals x to the n. Functions with exponents in them, or relationships with exponents in them, can be written in one of two forms: with an exponent, or by using logarithms to describe them. So I could just rearrange this into log base x of y equals n, but that's kind of unpleasant. I'll do the solving something. So I'm going to take a natural log of both sides of this, because if these two expressions are equal, then they're, as long as I've got positive results here, x to the n is something positive, so if x is positive, we're good. Natural log of y would have to equal the natural log of x to the n, which that looks like I just made it worse, but if you remember your logarithm properties, I can get rid of my exponent by rewriting it. Because logarithms are a different way to represent exponents, exponent rules are related to logarithm rules. And this right-hand side is the same as n times the natural log of x. So this equation actually started out solved for y, and now I have it in an equivalent form that isn't solved for y, but from this form, if we know our logarithm derivative rules, I can find the derivative of y by differentiating both sides of this expression. So I'm going to take a derivative with respect to x of both sides of this. I'm going to rewrite this y as f of x for a minute. Natural log f of x. And the derivative of n times the natural log of x with respect to x. So if I differentiate both sides, the derivative of a natural log function, that was that 1 over sort of idea, so I'd have 1 over f of x times the derivative of f of x, which I'm going to write this way then, just to save a fraction. 1 over f of x times f prime of x. And the right-hand side, n in this expression, n is a constant. It can be any real number. So in this format, this is just some constant multiple, and I'm finding the derivative of natural log of x then. So it'd be n times 1 over x. I should have done the same thing on this side, n over x. But if I want to find the derivative of y, find y prime. Well, I just have to isolate this f prime of x here. So I'm going to multiply both sides of this expression by f of x. Algebra stepwise. And then I've got f prime of x equals n times 1 over x times f of x. Well, that's n times 1 over x times, what was f of x? F of x was y, right? Now y, in this case, we did actually have this solved for y. Y is the same as x to the n power. If I write this out here, I get n times 1 over x times x to the n power. And since 1 over x is the same as x to the negative 1, this is n times, well, those are going to reduce a little bit. I've got 1 fewer power of x than I started with. 1 less than n is n minus 1. So using this implicit differentiation, we can generate this rule, and all that's required here is that n is some sort of constant as opposed to a variable, and that x is something that's, well, within the domain of natural log. So x and y here would both have to be positive, but x is a variable. We can let it take on other values later. If I put absolute value signs in this, actually the derivative of absolute value, natural log of absolute value x is exactly the same as derivative of natural log of regular x without the absolute value signs. Just the domain is different. So let me show you one other related derivative rule fact. This one will involve a little bit more trig. Since we did a little bit of trig review, I'll throw some trigonometry in there. Let's do arc sine. So we learned all those arc trig, the inverse trig function, derivative rules. Just said, here, memorize this. I believe that that is described in the textbook how to find these derivatives, but it's kind of a messy section in the textbook in my opinion. So let's say I have, let me put this back to black. Let's see, y equals arc sine of x, otherwise known as inverse sine of x. This is the same as writing the sine of y equals x. That arc sine is the inverse function to sine, meaning if y is the arc sine of x, then the sine of y equals x. Or just thinking about our trig stuff we were just talking about, y here is an angle. I'm just going to draw it in the first quadrant for simplicity's sake. And x is the sine value. Well, x would be it's a little bit weird because normally use, well, the y value is the sine value because it's the vertical part of this. Or just, if I have a unit circle with an angle of y, then x is the sine of y. Sine is opposite over hypotenuse. Sine of y is x over 1. There we go. And this side is, what, 1 minus x squared square root? In case we need it later. But thinking about this, if I want to find the derivative of this, find dy dx. Well, the derivative of sine of x is cosine of x. The derivative of sine of something is cosine of that something. And if that something isn't just the variable in question, with respect to x, it's not, then I need to multiply by the derivative of that something, that whole formula inside. So I could write this as sine of f of x, cosine of f of x times f prime. The right-hand side is derivative of x is 1. So again, what we're doing is taking a derivative with respect to x. On the left-hand side, we're imagining y as a function of x. Y is this whole formula, but I'm writing it as symbol y instead of arc sine of x. So here's our expression. I can write y prime is 1 over cosine of y. It's like, well, that's not the formula that we learned. Y is arc sine of x. Y prime was that 1 over square root of 1 minus x squared. If you look back at this diagram, if y is the angle in question and x is supposed to be the sine value, so I just put a unit circle. You can pick any hypotenuse you wanted to, but just so that I can have a side of this triangle with x, use a hypotenuse of 1. That makes the third side here square root of 1 minus x squared, just Pythagorean theorem. And cosine of y would be this square root over 1. Well, that should look like the formula that you had to memorize. Same thing works with the other inverse trig functions. It's just a matter of using some Pythagorean theorem thoughts to figure out what on earth, how you translate back this cosine of 1 over cosine of y into something about x to have it in a function of x like you had. But y prime is 1 over cosine of y is a perfectly legitimate statement. It's just that y was arc sine of x. So the cosine of arc sine of x is that expression. So in any case, this implicit differentiation can be used to help prove some of your derivative rules because it is just kind of an extension of chain rule, just seeing chain rule in different places where we had a y and thinking of y as being a whole formula, even if we have it someplace else, just using it symbolically so that we can eliminate some of the weird-looking expressions in the middle. Also helps prove our derivative rules. We can also solve one more type of problem with it, which is called a related rates problem. What related rates are, let me think about the terms. Related rates. So I've got something that changes and it causes something else to change, and they both have their own rates of change that are somehow related. Typically, they're related by some underlying formula relating the basic quantities. So what I mean by that is, as an example, I know we're going to talk about this in a second, but suppose I have like a balloon that I'm inflating. The radius is going to be getting larger, the volume is going to be getting larger, and the relative rates at which those things are happening is something that we could calculate. And it's also going to change depending on the size of the balloon. It's not necessarily going to be the same all the time over time. Both of those, volume and radius, would change over time as you're inflating the balloon, and we can talk about how the rates of change of those two individual quantities compare to one another at any point in time. So that's what a related rate is. We have rates of change that we're comparing to one another. Let me clear this stuff off. And let's get back to this thing. All right, so, a cube. We'll start with a cube. The edges of a cube get longer at a rate of 2 centimeters per second. So whatever this mystery cube is. Just imagine like you're in a weird theater, they're showing the cube. It's the new avant-garde movie. It's just a cube that gets larger and you watch it. And then you sit there doing math computations and they tell you that you're crazy. But edges of a cube get longer at a rate of 2 centimeters per second. We want to know how fast the volume's changing. Not just in general, but how fast the volume's changing at a particular point in time when the length of each edge of the cube is 50 centimeters. So you can see we've got this shape that's changing. The edge lengths are getting longer, and in fact it says the edges are getting longer at 2 centimeters per second, which when the edges of the cube get longer, like the length, width, and height are all getting longer, that means the volume's getting larger, and we know how to find volumes of cubes. So we could calculate it for any edge length, we could calculate the volume. That's easy. It's just whatever the edge length is to the third power. But if I want to talk about the rates of change of those relative to one another, then I want to write a formula that involves the volume and the side lengths, but thinks of both of those as whole formulas, as whole functions that change over time. And we don't have to write out the functions. We'll just imagine that they're, like we did with the y. It's like, well, I'll just use the symbol y, and I know y is a whole formula. I can find its derivative symbolically and deal with the details later. So the idea of what's called a related rates problem, we're going to be using implicit differentiation. We're thinking of symbols that we write as representative of whole formulas that we don't necessarily have to write out those whole formulas, because it's not necessarily what we need. But if we can relate a couple of quantities, and each of those quantities are really changing, usually over time, then we can talk about the way at which those rates change over time and how those rates change relative to one another. So looking at something like this asks us how fast is the volume changing when the length of each edge is 50 centimeters. So it's asking us for a rate. How fast is the volume changing? That would be a rate of change of the volume. How fast? It's kind of vague, but thinking about like over time, because the other rate that we have here is talking about the edges getting longer at a rate of 2 centimeters per second. It's like, oh, well, if the edges are getting longer per second, then I can think about how much the volume changes per second. It might not be a constant. In this case, in fact, it's not going to be. In some cases, it could be. But the edge length of something changing by 2 centimeters per second will make the volume certainly get larger. But if you can imagine like having a little tiny box and adding 2 centimeters onto each size and then recalculating the volume, it's going to be a little bit bigger. If you had a huge box and you added 2 centimeters onto each side, that's 2 centimeters of like a layer of thick paint all the way around, or like a slabbing layer of mud. That's a lot of mud to cover it with 2 centimeters thick if it was huge to start with. So you can kind of think of this volume as incrementally growing. You don't have to go a whole second at a time, but just thinking about what would happen over a second, you can see that if it was small to start with and you add that 2 centimeters, that's adding a little bit of extra stuff. But if it was large to start with, adding 2 centimeters in each direction is adding a lot of extra stuff, a lot of extra material to this cube. So identify what the rates of change are. We've got things that are changing. The edge length and the volume are described as changing. And so we can write an equation that relates those two, not their rates of change, but just how do you relate edge length to volume? And I picked this one because it's easy. Edge length and volume of a cube. Well, to find the volume of a cube, edge length is length with height. So all of those are the same number if it's a cube. So just that edge length to the third power. S here to the third power would give me V, volume. Right? Whatever letters you want to use. You could use like x cubed equals V. But I want to know how fast the edge length is changing over time. I want to know how fast the volume is changing over time and be able to answer questions about those things. Because thinking about just volume equals S to the third power. Well, that tells me how volume and side length are related, but I want to know this 2 centimeters per second. That's how fast S is changing over time. So S, this edge length here, is really a function of time. So S is a whole formula. Volume is therefore also a whole formula of time in addition to being related to S. So it's like a composition of functions. So as time goes by, the edge length gets larger, and as the edge length gets larger, the volume gets larger. So it's really a huge composition of functions, but we don't need to know the inner one. If I just write an equation that relates the basic quantities, I could write V equals S cubed, or V of S equals S cubed. But really what I want to know here is a rate of change, not the volume with respect to the side length, but I want to know how fast the volume is changing, like how fast the volume is changing. So how it's changing over time, like time-wise, speed, how fast it's changing. So what I'm going to do, I'm using these symbols here. There isn't any variable t that's mentioned anywhere in the problem, but let's just say that t is this time in seconds. If I take a derivative of v with respect to t, I don't know how is volume related to time. Don't know, but I know that volume changes over time, right? Because the side lengths change over time, and the side lengths make the volume change. So volume is related to time, and the side lengths are related to time. So I could actually think of both of those as whole functions as opposed to just being simple variables. I think of it as v of t and s of t. So v of t equals s of t to the third power. But thinking of it like this, and again, you could write v of t or just v, you could write s of t or just s, but we're taking derivatives with them with respect to t, time. And you'll see this done a lot. The t sometimes just isn't defined. When you see this t all of a sudden in these problems, like, what's t? It's time. The book is generally careful about that, but in a case where you're doing a bunch of problems in a row or reading a bunch, sometimes they'll just throw in a t all of a sudden in a description. It's talking about time in case it's undefined there. So this would be time in seconds. So that was the only time units that were used earlier. We'll just stick without doing any unit conversions. But if I want to know how volume changes over time, volume would be in cubic units of length. So since centimeters were used, without unit conversions, cubic centimeters, and edge length is just in centimeters. So the rates of change with respect to time would be cubic centimeters per second and centimeters per second. The 2 centimeters per second was in the problem. But from this, the rate of change of the volume over time, how fast the volume's changing, and how fast the edge lengths are changing, is represented by this. The left-hand side I can't really do anything with. V, I don't have anything. I'm just going to write it as dv dt, kind of like writing f prime of x. I can write dv dt or even just leave it like this. But on the right-hand side, to find the derivative of s cubed with respect to t, I don't know what t is. So think of it as s of t to the third power, or a whole formula. S is a whole formula, or a whole function that's raised to the third power, because s represents side length, and the side length changes over time. So decide here to take the derivative with respect to t, it'd be 3 times s squared, and then times, well, s prime of t, or ds dt. So this implicit derivative is another way you can think of it. Although it doesn't say s of t here, we're understanding by reading the description and seeing this v and s related that v and s are both implicit functions of time, or they're just naturally going to be functions of time. Whether we write out that function rule specifically or not is another question. I could say, oh, well, it's just a linear function of time because the edge length gets longer by 2 centimeters every second. It's a constant rate of change, but you don't actually have to write it out to do this problem. The rate of change of the volume with respect to time is 3s squared times ds dt. So the side length is s. ds dt is the rate of change of the side length. So here's the end of the calculus part of this question. I have a relationship here that relates how the volume changes over time, how fast the volume changes, to, well, on the right-hand side, you can see there's actually 2 variables in there. There's s, the actual current side length, and there's s prime, or ds dt, which is the rate of change of the side length. So finding how fast the volume's changing depends on not only how fast the side lengths are changing, but also the current side length. Or, like we talked about earlier, when it's a smaller cube, the rate of change of the volume is going to be less than when it's a larger cube. So in terms of answering this specific question, this is plugging in numbers. How fast is the volume changing when the length of each edge is 50 centimeters? Well, when the length of each edge is 50 centimeters, that's s equals 50. So I could plug that in. ds dt is the rate of change of the side length. That's 2. Or this is 50 centimeters that gets squared, and then I multiply on a 3 and a 2 centimeters per second. By the time we're done, we get cubic centimeters per second. And if you put the units in there, it all does work out well, but we get 3 times 50 squared times 2, which is, let's see, 2,500 times 6, 15,000 cubic centimeters per second. But again, just like starting at the beginning, again, what we just did here was we were given an expression that relates a geometric figure, so we know some relationships between the parts of those, a geometric figure that's changing in size over time. So every 2 seconds, the edges get longer by 2 centimeters, or for any number of seconds that go by, the number of centimeters increase in the side length is 2 times that number of seconds. Just our basic rate of change, 2 centimeters per second. But the edge length and volume at any point in time or for any side length is related by this. If I knew a value of time, I could find the side length and then I could find the volume. But just writing volume as a function of s and then realizing internally volume and side length are both related to time also because of this changing side length. So doing differentiation with respect to time, differentiating the volume, just writing out the rate of change of the volume with respect to time, and differentiating the formula for volume, s cubed, with respect to not s, but t, I get 3s squared times, well, however s changes over time. So if you want to, and I know this is going to close this out, but I want to write on this anyway. Let me make this red. So this is one way to write this. I could also think of having, instead of v equals s cubed, and then taking a derivative with respect to t, I could write v of t equals s of t cubed to kind of emphasize to myself. I know that in general, the volume of a cube is the side length to the third power. But the volume and the side lengths are both changing over time. So if I want to emphasize that to myself, when I'm thinking about rates with respect to time, like rates per second, per hour, per day, those sorts of rates, as opposed to cubic centimeters per centimeter sort of rates. Because I don't want to know the cubic centimeters per centimeter. I want to know the cubic centimeters per second sort of rate. if I take a derivative of this expression, thinking of, oh, volume is a function of time, so I don't accidentally write the derivative of v is 1. So it's like not with respect to v, it's with respect to t. So I could write v prime of t from that, the derivative of v of t. And on this side, the derivative of s of t to the third power, the derivative of some function of t raised to the third power with respect to t. You can maybe more easily see from this notation, like, oh yeah, that's chain rule. I'm going to have 3 times the original s of t function times the derivative of this inside, so times s prime of t. So the one thing that's kind of nice about, even though it's maybe messier looking, the fraction style notation of this slope ratio notation for derivatives, it matches up with the units at which things change. So centimeters per second, when I'm talking about this s here, ds dt, the rate of change of the side length with respect to time is in centimeters per second. You can see, oh yeah, the side length changes in centimeters as time changes by seconds. So the slope style notation matches up with that. Similarly, if I'm talking about dv dt, dv over dt, that's talking about how the volume changes, which volume is in cubic centimeters. And time, again, the only time unit mentioned in this whole problem was seconds. So dv dt is talking about cubic centimeters per second, volume units per time unit. So the slope style notation matches up really nicely with keeping track of what the units are. It looks messier. You're free to use whatever sort of notation you want. Realize that you're going to see a little bit of all of it through the homework and tests and stuff like that. Use whatever notation you want, but this slope style notation, the reason it is used and why it was kept around, all the different notations were kind of created independently in different countries back when people were working on developing calculus textbooks originally. They kept them because they all have their benefits. One of the benefits of this is you can really think about what are the input and output clearly, because you see them both, and what are the dependent and independent quantities that are changing, and think about their units. All right, so let's take a look at, I believe the next question I have here is the balloon question. But again, the idea is find the ways to relate the general quantities in the question and then take a derivative so that you end up with a relationship that involves their rates of change. All right, so scoot this little. All right, so after a spherical balloon is untied, it expels helium at 150 cubic inches per minute. How fast is the radius changing when the balloon has a volume of 500 cubic inches? So, a couple hints again, and I'll let you work on this. Yeah, we've got 15 minutes, so think about an equation, geometry thing that relates some of the quantities in this question, and then think about differentiating that with respect to time in minutes this time around, since we've got rates in cubic inches per minute, and see if you can figure out the general underlying structure here. As a hint, spheres, let's see. What aspect of a sphere are we going to be dealing with here? Surface area, volume, radius, something else? Yeah, volume. When the balloon has a volume of something other. Volume of a sphere. Yep, H. Yeah, 4/3 pi r cubed. 4 pi r squared is the surface area, 4/3 pi r cubed is its volume.
So let's take a look at this one a little bit. There's a few tricky parts to this, aside from just it's not as nice in numbers as 2 and edge length to the third power. But we have, just like last time, we've got a relationship about volume. And in this question, I can see that the radius is going to be changing over time, which will make the volume change over time. Is the radius getting larger or smaller? Smaller. All right, so the balloon is untied. The helium is leaving at a rate of 150 cubic inches per minute. Just in terms of symbols, this one here, cubic inches per minute, that's a rate that tells me how volume over time is changing. So symbol-wise, I'm going to call this dV over dt. And this is getting smaller by that amount. So if I wanted to give a value to this, I'd say dV dt is negative 150. And if I read this question, that's not just at a particular point in time, it's apparently always. It's a constant rate at which the volume is decreasing. The helium is leaking at a rate of 150 cubic inches per minute. The question asks us how fast is the radius changing? And then there's some other information given, but how fast the radius is changing, well, I'd also have that per minute, but the radius would be just naturally units without doing any conversions, would just be inches per minute. It would be shrinking by some number of inches per minute. But this is asking us to find a rate at which the radius is changing. So translating that, we're being asked to find the rate at which the radius changes over time. But it's at a particular point in time. The radius is not necessarily changing at a constant rate just because the volume is. Just like in the last question, the volume wasn't changing at a constant rate even though the edge length of the cube was. So we're going to find the rate of change of the radius at a particular point in time when the volume is 500 cubic inches. Okay, so we'll figure out how to plug in numbers later. But our end goal is going to be to find a value of dr dt, which dr dt is not in this, but our basic underlying quantities here, the things that are changing over time, are the radius and therefore the volume. So, or I guess the volume and therefore the radius, however you want to say this. But volume is a function of time. If you want to write it more explicitly like that, you can. And radius is a function of time. And the two of them are related. Let's see, r of t, I'm going to write it this way, to the third power, this way. So now I've written it explicitly that r is a function of t and v, volume, is a function of t. And we want to find how the radius is changing, how fast the radius is changing. So I'm going to need to find a derivative of this with respect to time, or differentiate with respect to t on both sides of this expression. I'm going to use the prime notation while writing this just to mix it up a little bit. But if I take a derivative with respect to t of the function v of t, that's v prime of t. Right? I take the derivative of v, I get its derivative with respect to t, v prime of t. On the right-hand side, that's a coefficient. So I know I'm going to kind of keep that, but then I've got this to take a derivative of. It'll be 3 times, just like the thing we did earlier, 3 times the inside stuff squared. So I'm going to have this 4/3 pi times a 3 times something squared. The 4/3 and the 3 simplify to make a nice 4. And then I've got this inside stuff. R of t is still squared, or the radius at whatever point in time we're talking about gets squared, and then chain rule times the derivative of the inside, which will be r prime of t in prime notation. This is dr dt, dr over dt, otherwise known as r prime of t. So I've got a relationship here between how the volume changes and how the radius changes, and it also, as you can see, involves the value of the radius squared. But this relates 3 changing quantities. This one happens to be a constant because it tells us the volume decreases at 150 cubic inches per minute. So this number is negative 150 all the time. The radius, it doesn't tell us. We're supposed to be finding this. Find this. So that means we must somehow know the radius at this point in time. And we have another number up here that we didn't use, which we need to use. But it's not a radius value, it's the volume value. However, if you know the volume of a sphere, then you can find its radius. It's just not a pleasant number. Agreed? We have a formula for it, in fact, written right here. If I know that the volume is 500, I can solve and get the radius. If I wrote this up properly earlier, I believe it's about 4.9-ish. But symbol-wise, if I know that 500 is the volume and I'm trying to find the radius that goes with that so that I can plug it in here, the radius at that same point in time, I'm going to do 500 times 3/4 divided by pi and take a cube root. So all of that, however you want to write it, I'm going to write it like I said it. 500 times 3/4 divided by pi and take a cube root. That lovely number should be about 4.92. Exact form would be that one, but just for something to think about, I have a value of the radius that goes with the volume of this. So it's how fast is the radius changing when the balloon has a volume of 500 cubic inches is the same as how fast is the radius changing when the radius is approximately 4.92 inches. So this is that number in approximate form that corresponds to volume of 500. And I'd need to plug it in here. Now, in reality, to get the most precise answer, I'd want to use the unapproximated form. But for purposes of just not going crazy looking at this, let's say I put in this number, which is about 4.92 in that spot. And if I want to find the rate of change of the radius, I'm going to do this negative 150 divided by 4 pi and that 4.92-ish number squared. So all of that gets divided by. So it will be a negative, which is good. My rate of change in my radius should be something negative if my balloon's volume is decreasing. See that? Okay, smaller volume of a thing that we're assuming maintains its sphere shape, then the radius must be getting smaller. So I'm not going to go through the rest of the number part of this, but again, this part in the box is where the calculus ends. This is the equation we've come up with that relates to rates. It also involves knowing a third thing, which in this case is the radius of the sphere. And that's frequently the case. The relationship between two things that are changing doesn't necessarily it's not just necessarily one as a multiple of the other. It could depend on some other quantity as well. All right, so we will continue a trig-related one on Thursday and some other trickery. I'll probably post a couple of questions in advance so you can think about them. A little tricky. All right, see you Thursday.